Alrighty, let's continue actually with the same example. So we are talking about having the equations, let's see, x of t was equal to t squared, y of t was equal to t cubed minus 3t. And if you recall, we had dy dx was equal to 3t squared minus 3 divided by 2t. Okay, so this question says, show that this curve has two tangent lines at the point 3, 0. I'm going to go back a page and just comment here that at the point 3, 0, we did intersect this spot twice, and we have one curve with the negative, or one tangent line with the negative slope, one tangent line with the positive slope. So this happens with parametrics. It wouldn't happen with a function, but it happens with parametrics. So I need to show that there are two tangent lines at the point 3, 0. So the way that I'm going to actually do that is I'm going to plug in, let's see, actually I'm going to solve for the values where we get the 0.30. So what that means is if x equals 3, I can plug the 3 into my x value, and y equals 0, so I plug the 0 into my y value. So let's start with 3 equals t squared. That means t equals plus or minus square root of 3, and this comes from setting x of t equal to t squared, setting that equal to 3 because my x value is 3. If I plug 0 into y, I just get out that t equals 0. So the question is, which one of those actually works? Is it when t equals 0 or when t equals plus or minus rad 3 that I have the 0.30? Well, if I plug t equals 0 into my x equation, I actually get out x equals 0, not the 0.30. So this does not work in this situation. If I plug in plus or minus rad 3 into t cubed minus 3t, we will get out y equals 0 like we showed right here in this table of values that we did on the first video, in the first page here. Negative rad 3 gave us the 0.30, positive rad 3 gave us the 0.30. Okay, so I know I have two t values where I get the 0.30. I'm going to plug each of them individually into my dy dx to get the slope. So I have dy dx such that t equals the square root of 3. That gives me 3 times 3 minus 3 over 2 rad 3. So I have 9 minus 3, or 6, over 2 rad 3. And I would like to rationalize. That gives me 6 rad 3 over 2 times 3 is 6, which leaves me with just rad 3. Let's do the same thing, dy dx such that t equals the negative square root of 3. So that will give me, when I plug that into my dy dx, I'm going to get 3 times 3 again, and then minus 3 again. And then I have divided by now 2 times the negative square root of 3. So when I multiply this out, I'm going to get 9 minus 3 is 6 in my numerator, negative 2 rad 3 in my denominator. I'm going to rationalize, and I get 6 rad 3 over negative 2 times 3, or negative 6, and my slope is the negative square root of 3. So as you guys know, to write the equation of a tangent line, that's my goal here, I need to find the equations of the tangent lines, I have to combine my point, 3, 0, with each of my slopes, which are rad 3 and negative rad 3. So my equations of my tangent lines are y equals the square root of 3 times x minus 3, and I could say plus 0 out here, but I don't need to because adding 0 doesn't change the equation. My second tangent line uses my negative slope, so I have y equals the negative square root of 3 times x minus 3, and again plus 0. Oops. And those are my tangent line equations. All right, let's move on. Next part is basically 6 formulas, not really formulas, but some sort of formulas, but things that you need to know about parametrics and vectors. First of all, the position vector is written x of t, y of t, and you'll see these hard brackets here, which you might have seen in another class, maybe last year in pre-calc honors, but we use them frequently, or we say that position is x of t I plus y of t j, and these are just denoting that, sorry, we have x, goodness, we have x here and we have y here. It's common to say it's basically ai plus, I don't know why this is working like this, bear with me. This is basically ai plus bj, if you recall last year that a and b are the components of the vectors, and I and j denote the x change and the y change. So then if you move on to velocity, all you have to do is differentiate the x and the y. So x differentiates to x prime, y differentiates to y prime. And then your position function s differentiates to velocity, and instead of x times I or x of t times I, you have dx dt I and dy dt j. To get to acceleration, once again, you're differentiating. So velocity differentiates to acceleration by taking another derivative. So you have x double prime of t, comma, y double prime of t, or the second derivative times I plus the second derivative times j. Second derivative of x, second derivative of y. So these are very basic things that you should know how to do from dating back to the fall when we first studied position, velocity, acceleration from a differentiation perspective. Okay, I just paused the video and I'm picking up again. I want to show you the distance formula, which should look somewhat similar because we've done something like it. If you recall, we did arc length, which took us integrating from a to b, and we had 1 plus the first derivative squared dx. So I'm going to show you, I'm going to add a page in here and show you how this and this are actually the same thing. So the way that it works is if you take the distance formula, which was from a to b of 1 plus f prime of x squared dx, that was actually equal to 1 plus dy dx squared. So we're putting it in Leibniz notation. Then that gives us from a to b square root of, and I'm going to change the 1 to be dx over dx all squared plus dy over dx all squared, and a dx here. And I'm going to go ahead and separate my numerator from my denominator. So I'm going to have dx squared plus dy squared, and I had a dx out here, and the dx squared plus the dx squared in my denominators, or my denominators of dx squared, are actually a common denominator, and I can square root them to get a dx out here. And now my dx's cancel, and what I want to do is build in a dt, because the distance formula in parametrics needs a dt. So if I have instead multiply by dt over dt, then I'm going to slide the denominator over to underneath. So I have from a to b, I have dx squared plus dy squared all over just a plain dt, and then a dt out here. If I put this dt up underneath the square root, I will have to square it. So I'm going to end up with this integral from a to b, and then in the square root we have dx dt all squared plus dy dt all squared, and then a dt outside. And this is exactly the distance formula. So I'm just showing you that distance formula in parametrics, arc length in non-parametrics are the exact same formula, just rewritten a bit to accommodate the actual formula that's necessary. So coming back over here, what you need to memorize for the distance formula in parametrics is just leaving dx dt and dy dt separated and in parametric form when you take the square root, or what goes underneath the radical is dx dt squared plus dy dt squared instead of the more traditional 1 plus f prime of x squared. So then speed, which is, as you know, the absolute value of velocity, is basically the distance formula without an integral. So this one I just want you to memorize. And then magnitude, again, which is the absolute value of acceleration, same as speed, is without an integral, just a square root, but this time it's the second derivative of x squared plus the second derivative of y squared, all square rooted.